6 is things that you should have covered in 101. So you just kind of go back and refresh on that if you haven't thought about it for a little while. But I will highlight a couple things from that. One of them is the idea, and we know this, that if we're looking at signaling, neurotransmitter, hormones, signaling in general, what we're going to have to do is we're going to have that receptor, right? So that signaling molecule is going to have to interact with the receptor on that quote receiving cell. Okay, the cell that's going to be activated or inhibited by that particular chemical, whatever it is, neurotransmitter, hormone, whatever. It's going to interact with that receptor. And that receptor is basically going to be a transducer, right? And what it's going to do now is it's going to say, okay, I've quote been activated, or inhibited, but anyway, I've been activated, and I need to set something up to happen inside the cell. So when we do that, right, we see that once we're activated and things are going on inside the cell, we could end up with multiple activities being stimulated not only within the cell, but depending upon which cell it is that we're stimulating, which organ, different things are going to happen then in different organ systems as well. So finding there's our receptor, we're going to transduce that signal, something's going to happen inside the cell, right? And in turn then that target cell is going to respond in some way. Now you talked about the cell junctions in 101. Remember tight junctions, gap junctions, desmos cells. Everybody okay with those? Yeah, I need to go back over those. Okay, all right. So think about those. When we're looking at communication, ways that we can have signaling going on to body cells, one thing we could have, of course, we've talked about this a lot now, is the electrical signal. You have something going on in the nervous system. We can release neurotransmitter, and that then can stimulate some effector. The other way that we can have cell-cell communication or communication between cells is by direct interaction of those cells. So we're going to talk about this a little bit when we get to the immunology part, and that is we can have cell-cell interaction, B cells and T cells directly interacting, and that's going to stimulate something to happen in that immune response. Chemical signals, that's referring specifically to the hormones as opposed to the neurotransmitters. So kind of be a little bit careful there, right? So technically, a neurotransmitter is a chemical signal, right? But they're probably going to ask you about neurotransmitter in those terms. And when you think about chemical signals, they're going to think about other things other than that. So read carefully. But this is what we have here. So we're going to release the chemical signal. And we know that that signal then could enter into interstitial space, could go into the bloodstream, could interact with neighboring cells, or could interact with self, right? So with that in mind, right, we know that we've got different kinds of signal molecules when it comes to their solubility. We have those that are hydrophilic, and we have those that are hydrophobic. Philic means what? Philic is liking or seeking, right? Phobic is against, right? So if you're hydrophilic, it means that you're water soluble. If you're hydrophobic, it's like, I don't want to touch water, right? So in order for me to circulate, I've got to bind to the carrier protein. I'm not going to be soluble in that plasma. So the receptor location then, right, is somewhat dependent upon the kind of hormone we have, hydrophilic or hydrophobic. And I say somewhat because receptors on the cell surface are definitely a requirement for the ones that are hydrophilic, right? But the ones that are hydrophobic may, depends upon, again, the hormone, depends upon the cell, etc., may interact with surface receptors as well. Okay, it does not have to be through the membrane and then be intracellular, finding the receptor in there. So it is possible for that to happen. So here we see it going into the circulation, of course, going over there and hitting our target cell. And as I mentioned, this is the classical example of what you see about hydrophobic, and this may be somewhat what we looked at going on. Is it? So you've got your hormones, going to be the carrier protein, going to arrive at the cell. It's then going to be offloaded and bind to a receptor that is intracellular. That's the classical way that they present it. And that intracellular receptor could be in the cytoplasm or in the nucleus, right? That part doesn't matter. But the ultimate thing is, when you think about the hydrophobic molecules, they are going to work with gene activation. Now you want to be careful though, because even the hydrophilic ones can cause gene activation. But if you pause for a moment and think about this, right? Because I just said they're going to interact with an intracellular receptor. You said that hydrophilic ones are going to interact with a membrane bound receptor. Why does it take, or does it take, I should put it that way, does it take a difference in time between hydrophilic and hydrophobic as far as activation goes? You're going to get a gene response here. This is what you want to be careful about. Both of them can alter gene expression, but the hydrophilic one is most likely going to take longer to do so. Because it has to bind a receptor, get things going on in the cytoplasm, you have to get over the nucleus, those kinds of things. Whereas with that hydrophobic one, going through the membrane, that's part of the process, getting the receptor, and boom, we're in the nucleus, right? Things can happen. That's going to be much quicker. But both of them can activate gene expression, or alter gene expression. Now, just like with muscles, we have agonists and we have antagonists. And again, just like with muscles, if we're thinking about agonists, what we're thinking about is it's going to stimulate the response that you would normally have with that receptor. Okay? If it's an antagonist, it is going to block the normal response that you would get from that receptor. So they're basically going to work in opposite directions, just like agonists and antagonists in muscles do. Okay? So we can see a similar kind of thing here as well. Okay? When you look at how these hormones may stimulate the cell, right? So obviously we don't have just one hormone out there at any one time. We've got multiple things out there in circulation. One thing is that two hormones could be additive. And if they're additive, it's just like we were talking about with those IPSPs and PPSPs. They are truly additive. So A plus B, right, is really whatever I get with A plus whatever I get with B, that's my total, right? It's not a subset. It's the total amount. So they are indeed additive, right? If it's synergistic, though, you notice that what happens here is one hormone, I'll use the word gives permission to another hormone, so that activity is actually beefed up quite significantly compared to what would be there otherwise. But you notice that they're not fully additive, okay? Not fully additive. So we're looking at regulating things that happen inside of cells. We said about we need the receptors to be able to do that. We could have a situation where we can upregulate or downregulate, so increase or decrease, the number of receptors that we have in a given cell. So when we look at upregulation, we're increasing the number of receptors. When we look at downregulation, we're decreasing the number of receptors. And this is something that happens really without you thinking about it. So for example, if you are on a high salt diet, so if you're one of these people that just sits down at the table, either reaches for the salt shaker, puts 10 tons of salt in your food, right? What are your receptors going to do? Eventually they're going to do what? They're going to say, enough is enough. I'm going to downregulate. I'm not going to be stimulated as much as I might. Okay? On the other hand, if if you're on a low salt diet, so you're not a person that salts your food, everything is quote natural, if there is such a thing, but anyway, so you don't get anything. In that case, you're most likely going to have an upregulation increase in the number of receptors because in that scenario, your body is basically looking for all the stimulation it can get, right? So it's not getting enough, so it wants to get a little bit more. And the first example was like, this is an overload, and I gotta have a way to be able to tone this down a little bit, okay? So we upregulate or we can downregulate. Now, going along with that is the idea too that we have at the receptor level affinity and specificity. And this you probably remember from chemistry, right? So affinity is what? Basically ability to bind, right? So affinity is how well, right, is that hormone or that signal molecule going to interact with that receptor, okay? Specificity tells us the opposite part in the sense that, hey, you're not the right molecule for me, right? So therefore, I don't care what your concentration is, you're not going to bind, right? That's specificity. But that may be a bit of an exaggeration too, for the simple reason that concentration can have a big impact on specificity. So in other words, we have insulin receptors, right? We all know that, we all know that. So we expect they interact with insulin, right? But there's also insulin-like growth factor, IGF, insulin-like growth factor, that can bind to insulin receptors based upon the concentration. So if it's at a high concentration, right, it may interact with those receptors. So there's always a bit of an exception to a rule. That's my point, okay? Now, when you're looking at the synthesis pathway, the stimulation pathway, the synthesis pathway inside the cell. So we're looking now at, can we have an impact on how that signal molecule is going to be utilized by the body? Well, one way we could do it is we could change the synthesis level. We could put out more, we could put out less, right? And we do that all the time with our hormones. We never take them completely away, but there's more of them or there's less of them, right? So we could change the levels, we could change the synthesis. We could also change the amount that's bound at any one time. So that too would be a way to say, basically, I can transport 10 molecules of whatever it is, X, with this transport protein. And, I'll bind all 10 and, all well and good. So the amount bound is another way to think about it, and that also goes along with the amount that's bound to the cell, right? Because what is inside the cell doesn't count as free hormone, right? Okay, it can't interact, it's already doing its business. And then finally, we can think about breakdown, of course, and that's just something like we would turn it. So if we turn it down, turn it off, turn it over, break it down, that level, of course, is going to go down accordingly. Then finally, we can think here about things that happen inside the cell. We probably talked about this, permeability, big thing, metabolism, big thing, right, inside the cell, as well as gene activity. So that should pretty much all sound familiar. There's a couple more things before that should sound familiar. Are you okay with that so far? That kind of ringing bells? Yeah, I don't see heads nodding. Yeah? No? Yeah? Okay. Now, there are a couple other things to mention to you, and that is that when you think about stimulating a receptor, it doesn't have to be a chemical stimulation. There are other things that can stimulate receptors. So if you know this, we could think about what's going on with the eye, which we will with the special senses, right? So we can have the opsins and so forth associated with light pathways, photons of light, very, very different. The hearing organ is going to be based upon sound wave, so a pressure wave, okay? And then finally, the pressure in the chain muscle. And this is a situation where what we're looking at is an encapsulated receptor. And we're looking at an increase in pressure, increasing interaction in that receptor. And I'll show you that too to get that for. things that is very important as far as how we're going to, work with this hormone. We only have a limited number of hormone molecules, we want a lot of things to happen. So that's this, and that is when that molecule binds to the cell, it can stimulate multiple things to occur inside that cell. And that's called amplification. So they put some numbers on here for you, so you can see, right? Let's start out with 1 and end up down here with 10 million. Big difference, right? And that's because along the way, I've started to stimulate multiples, not just single, not, one way. I stimulate multiple things, and that allows many things to happen inside of the cell. So signal amplification allows that to happen. Different perspective on it here, same kind of an idea, right? You end up with a lot of things going on here, right? We start out with just one interaction up there. So that's what I want you to get out